Thanks, everybody, for joining us. We got a few more folks coming in, but we'll start with some introductions. I'd like to thank everybody who's joined as an attendee, particularly our LPs. We're hosting this webinar today on the digital physical integration. Got some really exciting guests that we'll introduce to you in a second. But the whole idea around this space is we're at this kind of linchpin where the digital and the physical are truly integrating to kind of create the revolution that we're going to see over the next decades as we head towards things like lights out manufacturing, currently labeled as smart factories, AR, VR interactions for human augmentation. There are other acronyms like IT, OT combination, which is information technology and operational technology, all these things coming together to really kind of truly move the world forward. And Prime Movers Lab really this is our key focus of how we're investing in this deep tech. So we're really excited to kind of bring together these three fantastic founders to walk through what they see as the next couple of decades in this integration space. My background, I'm Bryan. I'm a host for today. My background's in manufacturing. Been very passionate about this kind of space since it was termed Industrial 4.0 or I 4.0 back in 2011-ish. And it's only grown from there with the digital twinning and other technologies and integrations that have kind of come along. I'd like to introduce Alessandro, my co-host for today.
Yes, thank you, Bryan. Alessandro, I'm an electrical engineer with focus on analog electronics and ASIC design. I got a PhD in robotics and innovative technologies. I've been working on a smart skin for soft robotics. I went to Stanford, was a researcher, material science department, working on organic electronic transistors. And then I started my own company, SimPlus. We were developing touch and force technologies for sensors for LCD and OLED displays. I worked with some consumer companies, and then we pivoted towards automotive. I worked with the major automotive tier 1 and OEMs, working to integrate our sensors into tech automotive products. And I would like to ask our panelists to introduce themselves. Let's start with Andrew, co-founder and CTO of one of our portfolio company, Venus Aerospace. Please introduce yourself and tell us more about you.
Yeah, great. Andrew, CTO and co-founder of Venus Aerospace, and we're designing a space plane to enable 1-hour global travel. And I've had a large range of spectrums throughout my career, everything from being a mechanical engineering professor for about a decade, down deep in R&D, all the way up to, as an officer in the Navy Reserve, I repair ships down in Japan. And then kind of everything in between with, I'm on my third startup, if you will, and one of them being a rocket company with Richard Branson. And so different aspects of each part of that phase require a whole bunch of different combinations of digital and physical infrastructures. So we're really looking forward to the conversation.
Great. Let's go with Samuel, CEO and co-founder at Fort Robotics. Tell us more about you.
Hi, Samuel Reeves, founder and CEO of Fort Robotics. Fort is my second robotics company. First one was called Humanistic Robotics, and we built autonomous landmine clearance robots, and they were big enough to kill you, and they were running AI, and they were working around people, and that was really where we discovered the kind of unique safety issues associated with this next generation of automation that we're seeing in a lot of these manufacturing scenarios. And so what we found was it took us a really long time and a lot of effort, and it was really tricky to provide the safety for those machines. And so, as we see that kind of trend replicate across all of these environments like we're about to talk about, we saw a huge need for a communications and control platform for all of these scenarios, for all smart machines. And so that's why I started Fort a few years ago, and now partnered with PML to scale out a communications and control platform for the next generation of automation. So all machines are becoming smarter, and so the communications and control needs really transform from there.
Wonderful. And Will, your turn. You're the director at MODICA. We know that you build also a solution for traditional manufacturers, and you also have a container boat. So tell us more about yourself and your background. We will talk more during our webinar.
Yeah, great. Thanks, Alessandro. Yeah, I'm Will. I'm co-founder and CEO of MODICA. We're a startup in Seattle that turns shipping containers into modular microfactories and workspaces. The overarching goal of that is a bit deeper. It's to make systems integration of industrial equipment and workspaces a little bit easier. My background is in robotics and automation in aerospace, food processing, and some other realms. And my previous startup was a small systems integration consultancy where I learned a lot about how much duplicated effort there is in that field. So we're trying to make it easier to build factories and deploy them.
Wonderful.
Thanks, Will. Well, why don't we just dive right in? I mean, for me, like I said at the top, the whole space in 20 years is how we get to a lights out factory where something gets put in on the front end, a whole bunch of robots, automation, other thing like that, come along, build it, whether it's a plane, whether it's a house, whether it's your coffee maker, and at the end it just gets shipped out automatically. That kind of philosophy, or whether it's a service center where you just drive your car in, leave, it does all the servicing, lights out, and you come back in an hour, it's completely refurbished. Those kind of things are where we really truly are the end game for this digital physical integration. I'd like to get all of your opinions on kind of where you think this is going, and what are some of the kind of key steps that are going to take us to that kind of 2040, 2050 state where robots are a key part of our everyday life. Why don't we start with Andrew and just work our way through that and give us a...
Sure. One of the ways I look at it is where can you remove the human? Both from there's a cost element there, there's also an error element. And so certainly if your business model is all about how do you drive your production costs low, then what you described, right, of the automation, the lights out, makes a big difference. In one of the industries I've been in the rocket industry, it's actually all about how many billions did you spend developing the product, right? That's actually where your cost model drives. And so it's a fascinating change there. Where you need to remove the human is finding of the information. If someone is copying and pasting, say, a part number from one source of information into a PO, into a work order, into, like, errors can creep up, as stupid as it sounds, in that, and then the chaos that ensues can be crazy. So, right, it's the areas of where are you removing the human, and where are you automating things, and where is that the best bang for the buck? And certainly, as new technologies are coming forth, whether it's additive manufacturing or yeah, all the way to lights out, it's different parts of that same larger problem of reducing human errors and reducing the layer of communications necessary for progress to happen.
So you're talking around like PLM systems, product lifecycle management type systems. It kind of sounds like, where do you see that kind of being deployed within Venus, and how does that form part of your business model?
It's a key part of our development that we're focusing on, because there is no one system to rule them all, and it depends on, let's say, how, what system are you using for your CAD, right, your computer aided design, and then what system are you using even to buy parts, and how are you talking between the two? It's all these problems that don't scale, right? All of a sudden it's like, great, let's go hire another 100 people, or let's go buy another 1,000,000 parts. Any of these things that don't scale well, or some simple error all of a sudden throws in a 6-month delay because you got something completely screwed up. So we are developing our own internal software, just like a couple of the companies in the past have done. And so it's both to tailor that flow of information, so there's one source of truth, and then other systems can refer to it. And it both is, if something has to change, if there is a design change, it happens in one place and then can spread out. But it's also, like I said, it's to minimize the errors, because right now, for Venus, right now, we're heavy in that early design phase. And so for us, we have to right now build up that infrastructure so that we're not simply copying and pasting and hoping everybody does a good job in minimizing errors, right? That's the things that lets you actually accelerate and enable right now. But that then lays the groundwork as we start getting hardware heavy, right? That you're then able to push forward on some of the automation.
That's a really key point to a lot of this, is that kind of upfront investment and upfront time to get the systems right, which is where the integration comes in. Will, I'd love to get your kind of take on how that integration kind of works when you take that data flow that Andrew was talking about and take it out onto the factory kind of positions.
Yeah, definitely. And Andrew, I love that you mentioned single source of truth. We talk a lot about that here. In our case at MODICA, we we lean more hardware, but we're beginning to lean more software, but we're figuring out where the software gets embodied or where the hardware gets encoded, I guess, and what we're all looking to as we develop things. I guess when I think about digital and physical integration, I think about, you know, how software is kind of getting absorbed into hardware and where hardware is getting absorbed into software, and the software being applied onto hardware is that's Industry 4.0, that's industrial IoT and IoT in general. And I think there's an arc from sort of Industry 4.0, which I like to think is in a lot of cases adding intelligence to machines or adding things. But I think there's kind of Industry 5.0. I know other people think differently about this, but the way I see that is there's going to be next generation of machines over the next few decades as old machines get replaced that are inherently intelligent. It's not an add-on. It's not a company adding sensors. It's just already there. It's just embedded. So that's kind of an interesting arc on a longer horizon that we pay attention to. And then the other really interesting area is where it's sort of less common, I guess, but where hardware is absorbing into software. And this is some interesting areas where we're relevant because there are products. So there are companies that started software only. So one example we were talking about recently is Snap, you know, with their glasses. This is basically a software company, a social network that is getting into hardware to embody their product. And there are a lot of examples like that. There are examples of AI companies that have taken basically just algorithms and now they need them to be embodied on a chip, you know, ASIC or an FPGA or whatever it is, and you need to manufacture that. So that's an interesting area of interfaces we think about a lot.
Nice. Yeah, that longer arc, that Industry 5.0 that you mentioned, there's a lot of moving pieces around in there. You know, how do you get the return on investments? How do you get the right? Do I drop in additive? Do I drop in some AR, VR? How do I bring the human aspects into that? I think that's kind of, just to roll on, I think that's kind of what you were mentioning, Samuel, with your early kind of transition is you've got these stacks of both physical and digital. How do you keep the human interaction in that space? And I'd love to kind of get your take into that.
Yeah, you know, as you were talking about the lights out factory, was one of your original questions. You know, I was thinking, you know, that really implies two things. It implies a high level of automation for one, and then a high level of connectivity with the rest of the world is kind of the two things that you would really have to achieve to have a lights out factory. And we can talk in a second about whether the lights out factory really should be the goal or not. But just with your original question, I think there are a couple of elements there. On the automation front, you know, my sense is that the high volume, low variability type of scenarios have been pretty automated for a while. And it's now like automation flowing out to the long tail of goods that will enable that kind of lights out factory function to be more widespread. But then the connectivity to the outside world, I think we're just beginning. I mean, I think, you know, we're all used to, I mean, we're having this webinar over Zoom, right? Like it's a you know, a basic truism that we live our lives on the internet. But I think for even some of the most automated factories, that is not necessarily the case. So I think there is a real divide between IT and OT that's going to have to be bridged for you to have that lights out factory. So I would say, like, my sense is we're early in the journey of widespread automation and early in the journey of IT and OT merger. And so I don't think we're going to get this widespread lights out factory for quite a while, but I wonder if that's even the goal. I mean, I think when we look at, you know, the kind of machines I was talking about that are mobile, that are, well, putting mobility aside, that are dynamic, that are reconfigurable or mobile, that are running AI, that are connected to the internet, that are working around people in shared workspaces, like that's kind of the smart machine of the future that we think about a lot. And those machines are all kind of like the new coworker, right? And so I think we're going beyond lights out to like human augmentation. which I think is super exciting, because imagine if we were all be able to like go to work in whatever scenario and just have our effort compounded like 10x, you know, whatever job it is. Like maybe that's the industry 5.0 that Will was getting to. But I prefer human augmentation to lights out, because I think it's a more exciting scenario for society. But I'll stop there. I forgot your second question. You asked me the second question. I answered the first question.
It's okay. It's okay. Alessandro, you want to jump in quick?
Absolutely. So of course, in this digital and physical integration, you know, there are many benefits, but for sure there are also some key pitfalls. Based on your experience, tell us more. What are the pitfalls of this integration?
Are you addressing that to me?
Yeah, you can go first.
Oh, sorry. I thought you addressed something else. So the integration that we're concerned about is specifically the element of ITOT that involves action in the physical world. So control systems like OT, traditional OT, are really geared toward generating action in the physical world. They're not geared toward global scalability across networks that are traditionally built for IT purposes. And then when you look at the IT world, fantastic at circulating information around the globe in a whole bunch of media, but not built for actuating the physical world. So we've built this safety and security focused communications platform that lets those two worlds come together in a machine and in any other kind of endpoint that a machine needs to talk to. So examples of that would be, you know, autonomous tractors in the middle of a field in California needing to communicate back to a command center somewhere across the world. Like, you need a control system that spans the internet instead of a control system that spans that tractor, because you need to get the data, but you also need to be able to actuate the physical world. So there's a common theme in, you know, smart tractors, autonomous golf course mowers, autonomous forklifts that require, you know, that kind of communications and control. So just in that use case, like human monitoring of machines that they don't sit in the cab anymore, you have like the merger of IT and OT. So that's where we spend a lot of our time.
Nice.
Yeah, nice.
I would kind of jump in, and Samuel, that's really, I kind of want to, I'm very interested in this idea of kind of maybe dangerous commands or dangerous feedback loops. We've thought about this, but yeah, that's something that keep top of mind. In our experience with digital kind of physical integration, you know, one of the, I guess, the benefits first, you know, one that comes to mind for us a lot is we have a saying at MODICA that V3 is V1. You know, when we're building hardware, it's like the first thing we drop into CAD rarely, you know, works. We need to iterate. And what is great is that we also have a new principle where V1 should be almost strictly digital before we start even making anything, you know, between CAD, between multi-sim, between all kinds of approaches we can take to validate. We can cut down cycle time for prototyping and validation. And that's been huge. It also helps us visualize things. You know, when we center on digital versions of hardware that we'll be building, it's easy to share out to stakeholders. That's really been an accelerant. I guess to quickly touch on one of the pitfalls, Alessandro, as you asked for, is there's a lot of, when you start adding sensors to things or machines become inherently cognitive, or they're collecting data, you can drown in data. That's something we've found in working with clients, is making sure you're measuring the right thing. You know, capture all the data for sure, but have a strategy in place for doing something with it, or at least handling the massive amounts. I think that kind of actually plays into what you're saying, Samuel, about making decisions and then acting in the real world. You need to make sure you're acting on the right data and looking in the right place. Can be overwhelming. Data can be overwhelming at this point.
That's a good point. They say data is the new oil, but at the end you need to extract information, meaningful information from data. How about you, Andrew?
Well, what comes to mind is immediately is like hazardous testing, whether it's a rocket engine or something like this, right? There's a level of, if you go all the way back, there's, we need to test early and often and fast, right? Any new development you're doing is just a pile of testing. And so you can drive the thought towards, well, let's automate the testing platform and let's automate both the ability to do the test and then get the data and then do all the analysis, right? And so you can focus down there, but if it's hazardous testing, there's still a level of which, yeah, but are we sure? Like, as an example, the control system says this valve is closed. Like, do we know that, right? And how well do we know that? And what's the consequence of a false positive, or what's the consequence of the different system that can happen? So, you almost always in those hazardous systems will have some sort of manual override or something like that. And depending on what you're testing, you can get into a system where the actual thing that's delaying your test from being as fast as possible is the fact that in the end it's hazardous, and you still need, right? You still need the procedure and the check and the manual system and eyeballs on target. And then you talk about, well, we want to tweak the procedure. Well, what does that take, right? I have a friend who's doing a software update for, a Navy fighter, and is it that they're terrified? They're like, no, we found the line of code. This line has an error. We need to fix it. But no, you don't. The entire software stack has gone through all of this certification process and all of these things. Like, I don't care this one line that you need to tweak, that the consequence of any change is this following cascade. So sometimes the problem is literally in change management, because what do you say, version 3 is version 1. So how do you design the software hardware stack up that you can then, when you're wrong, not if you're wrong, when you're wrong, how can you come back and change quickly, safely, with the right level of supervision, right? And that oftentimes can be one of the hardest loops to solve.
That's a really interesting point, and one a lot of particularly non-technical people have a hard time getting their head around. How do you, with your founder head on, think about the financial justification of that upfront loop and doing some of your kind of returns on early investment into that integration space? And how do you really own that as the right thing to do versus something that should have been or should be done later? I'll just open it up to anybody who wants to jump in.
I think I'll start. It all piles together, like all of our life experiences. We all remember all the pain points, right? In fact, there was I remember talking to a machinist programmer, and someone finally said, why are you programming with this kind of a tool offset? And it was like, well, 30 years ago on this one machine, it cost him like $1 bajillion the mistake I made. And it was like, wow, but those machines have, like, that error is now no longer possible. So some of it is our life experiences that come to us as these pain points, and right. And so I think one of the harder problem as a founder when you're early on is to recognize what is just a pain point and an experience you don't want to recognize, but is actually a problem that you need to avoid, or has technology or process or systems gone to a point where the probability of that happening is now low, and that you're better off actually investing in this real problem that's going to be different, right? And so you end up making a judgment call, but it's often we want to make decisions that are based on real data, but oftentimes it's I've heard it said, right, we pretend like we're logical beings, but in the end we use logic to defend the emotional decision that we've already made. Right.
Nice. Yeah, that traveling knowledge gets built in so many places, and is probably a key bias that gets built into a lot of this integration stuff that happens along the way, whether it's intentional or not, that's making it the bias. I'd love to get your take on that, Will, because you're kind of building out these factories that are intended to be mostly integrated.
Yeah, definitely. I guess to speak on, as a startup and as a small company and a founder making decisions on technology integrations, it's actually a good pressure for us to have, kind of having limited resources and limited ability to absorb some risk. I love the idea of connecting everything and trying every tool that's available to us to help us internally have great operations and succeed with what we're doing, but we have to kind of put the brakes on sometimes. this is a core problem that MODICA is trying to solve, is reducing risk and costs and timelines for integrating technology systems, whether it's machines or software, where they come together. So it's a problem we're working on. I don't have the silver bullet yet, but I think some of the things we're doing in terms of making the systems integration challenge, whether you're doing it by yourself or you're paying a third party to do it, a little less risky. Trying to put bumpers on that process and also make it faster.
Just while you're on that, really kind of go down that a little bit further. What kind of explicit versus implicit feedback are you getting from your early customers on what they think their challenges are, but what versus what the real challenges might be?
Oh, that's a great question. Yeah, I mean, everything on first conversation, I guess the V3 is V1 applies also to discovery, customer discovery and problem discovery. The first time you ask, you might get, we often do get a top level. Also, if we're asking further and further up the chain, the answer changes, but there are a lot of assumptions, and actually data, when we're not overwhelmed by it, is a great way to work with the client to really drill down on problems. So, they could be complaining about integrating a 3D printer with a CNC mill and like getting parts between them. But as it turns out, it's the throughput of any one or the other machine that's really their hang up, and we can see that in data. So I'd say in terms of implicit and explicit, we usually just we fall back on data and proof and try to be pragmatic about quantifying the problem, because people have a lot of feelings and opinions, but we want to collapse it down to metrics.
Nice.
And Will, at your company, which technologies and tools are you using to facilitate the digital and physical integration?
Yeah, well, in a lot of different areas. One is, one thing we like to say about MODICA is we're hoping to be able to basically grow digital factories around the parts as they're designed. This is kind of a long arc group of capabilities we'd like to have. But everything starts with basically a 3D model, and we go from there. The 3D model ends up being made by 3D printing. We work heavily in additive, but across a broad spectrum of digital manufacturing technologies. And then as a third tier, we work with custom automation and custom tooling and whatnot. So we kind of go in gradations from the pure CAD models to digital native manufacturing technologies, CNC and additive, and then on from there.
Yeah, your question is a good one, Alessandro, about how IT and OT might have to coexist within a startup company. And it's something that we've both had to build intentionally, and also something we've had to kind of storm through, because the two sides don't really understand each other. Back to Andrew's comment about updating a line of code in a fighter jet. But the way to be a communications and control platform for the machines of the future, that really draws from the best of control systems and then the best of IT. Our CTO comes from high-speed networking. The use cases for that traditionally are, watching movies on your TV at home, streaming, high bandwidth video. That really needs to be perfect for you to have a good experience. But then we need to apply that to these kind of control systems where, if you tell it to do something, it has to do it, like up to 10 nines of reliability, which is like double the level of reliability of our typical communications networks, right? So we had to build a hardware team and a safety architecture team full of people from automotive control systems and aircraft control systems. And these two sides, best people in the world still don't completely understand each other. So it's like a constant storm every day, right? And I think when you look at that kind of extrapolated economy-wide or globally, that is the challenge in IT and OT integration, where the IT world has interoperable platforms with just a few standard platforms for each category. and you have inanimate objects that are easy to integrate, that are standardized with standardized training, and they turn over like, you know, every few years, right? The whole thing gets refreshed every few years, unless you're like a bank, right? And then, you know, on the other side, on the OT side, like nothing is interoperable. That's an extreme case. It's a little bit interoperable, but not like, you know, our IT systems. Super fragmented. They're not inanimate objects, they're moving objects. There's no like standard Cisco training course for them that's like super widespread for thousands of people every year, you know, and they don't get refreshed. Like these machines stick around forever for like decades and decades and decades. So, you know, you have a lot of challenges taking older plants and older production scenarios and refreshing them. It's not like buying a router and put a new router and putting it in your office. It's like going machine by machine and making a decision of like, really, should this go on the internet and how do we do that? And it like might not even speak any kind of modern networking language. So do we really need it on the internet, and do we have to replace it? Can we adapt it? So, you know, we see the challenge in developing our own systems, and then, you know, it kind of makes it like super obvious about the challenge that's going on globally.
That's a really valid point about the kind of cost differential between the IT and the OT side too. Kind of the 3-year cost cycle versus the 30-year cost cycle for machines and the investment. That's a big challenge for a lot of this kind of integration that you go along, because you're usually a lot longer committed to something that's in the physical space than you are to something that's in the digital space. Although I've seen machines that still ran on Windows 98, so you know, you got some of that trails along with it. Just want to take a quick break for any of the LPs or any of the other participants that are in there. If you have any questions, please pile them into the chat. We'd love to make this an interactive session, trying to answer anything that's kind of coming to your mind as we made it through the first half an hour of this webinar. Until we get some more questions, we'll just keep piling on with where we're going. And I kind of want to just pivot a little bit, because one of the things that Andrew touched on a little bit on the early is this trend towards the digital twinning and that kind of creating a really usable MPV in the digital space. I just kind of want to get you guys' opinion on, you know, is that a big driver, or is that just a current trend that's going to kind of move away as we get more heavily integrated into the space? I'll let anybody jump in.
I would say huge trend, like clear ROI. Like,
how do you use digital twinning at Fort? Do you engage much in digital twinning?
We don't do that as much as we are building a communication system that enables the physical world to get connected to the digital world, and that's a critical requirement for a digital twin, because you're not gonna connect all the digital data and process it and make all the decisions in the same physical space. Like you need the OT to be integrated with the IT for that to like really take root. But we don't. I mean, Ford is
you're a key unlocker to that.
Yeah, more of an enabler.
And Andrew, are you got kind of opinions on where digital twinning and all that is going?
It's a natural progression. I remember a sea story, a friend, sailor in the 90s arguing with someone in DC, and he's like, no, you sent me the Mark III part, I have a Mark II part. And the message eventually came back and said, no, you have the Mark II part per our database. Great. And his whole story was, at least in 2012, I could take my cell phone and take a picture of it and send it back to him by email and be like, no, look, it says Mark II. Right. So as information transfer has increased, it's enabled that. But now we're talking about like, no, the digital record is actually truly updated and live. And so right, the last step of someone repairing a ship as they drop in the Mark V now is that it's been updated, or it's talking to the system that's yet verifying it's a Mark V. And you know, I can even think that as even on assembly lines. So before we even talking about how smart this part was made, right? If I have an engine, I need to be able to say like, okay, well, this is my engine, and what serial number was it, and what was the torque spec that was put on that thing, and then that wrench. So even getting all of that information live and knowledge, and it's going to be different on the serial number 2 than the serial number 3. So just tying together all of that information, right? How far you can push that information chain is a tremendous speed up, right? Again, it reduces the errors and it speeds up the flow of information. And anytime you're doing something massive, right, communication goes like n squared with the number of people, and so you're pulling back that front of how right, how far does information have to go before you're finally having to break out of this digital twin, and it's a natural progression and high ROI.
How do you create a feedback loop from the physical space over time back into that digital twin to ensure that you're getting more and more precise with it?
Yeah, absolutely. I mean, with everything performance parts that comes back in with it, now it's performance data. It's now how did this engine do on the test stand, and that engine, the test stand data, then fed back into the model that's talking about the serial number 1 vehicle or serial number 5 vehicle. And so you know exactly how the performance of the entire system goes down to, right? So it absolutely ties back in. And then even down, now you're down in the operational side of the world where it's operations and maintenance schedules and all that, right? And performance degradation maybe flags some sort of maintenance that needs to happen earlier, or you can delay that, right? I've had conversations with in the Navy talked about, like, can we push out that maintenance cycle another 6 months to make sure we can get back out to sea and complete this mission. So all of that can be more data driven than opinion driven.
It's a really interesting point. Will, if you look like you want to jump in on that one.
Oh yeah, no, it's great. I think a few threads have come together. First of all, I kind of love digital twin, just conceptually. Like, I'm a very visual person, and something I've done ever since I kind of heard this term coming around is try to tie it back to, like, okay, what is it conceptually? And to me, it always is an extension of SCADA and just data collection. It's like I worked for a wind energy company a long time ago, and I built a Visio diagram that was tied to real live data from a wind farm, and I thought that was really cool, and it was. But that's digital twin. A couple thoughts I have is, one, it absolutely accelerates a lot of things. It accelerates stakeholders seeing things, accelerates responsiveness when something goes wrong. I think I just had this idea when you were talking, Andrew, about we talked earlier about mass customization, or I was thinking about mass customization earlier, and this is kind of the reverse. It's kind of like, instead of every part that's coming out of a machine being unique, it's how every machine wears over time and can perform differently, and how you keep tabs on that. The other thread that I love that tied back in is, I was thinking about how digital twin is also susceptible to this. It's kind of the reverse of what Samuel was mentioning earlier, where you have a command that might do something in the real world. The reverse can be true if there's some kind of delay in information. If you're relying on digital twin, you need to make sure that twin is being updated to reality accurately and quickly enough.
It's how do you kind of, as you're building out like a micro factory, how do you decide which pieces of the capital to put into that A, digital twin, and then B, into the actual physical space that comes along with that? What are the kind of decision points that work that cycle? Do you just completely cycle a digital twin to do that, or is it a?
Yeah, everything. So for our microfabs and our other systems, I mean, everything is basically digital twin. So we kind of monitor everything, and some of them are, if we want to think in a more visual sense, a lot of them we use. So for our what we call our robotic interposers, which are the robot arms that can move parts from one machine to another, we use digital twin to obviously analyze robot paths. We use offline programming to check for collisions with machines. And to do that, we need to have completely accurate models of the machine tools that are in their pods, the robotic interfacers, the whole structure that they're sitting in. So we try to get our hands on, with our partners, OEMs that produce 3D printers and machines that we work with, the more accurate the model we can get from them, the more accurate our digital twin can be. And it's getting there. CAD models of virtually all the robots we use, we can get them from the vendors if we beg enough. And increasingly, those models are becoming available.
Nice.
Great. And so what's the role of humans in this in this process? We are trying to automate, the simulation, the digitalization of processes, but at the end there is still the human as a central role in an organization, and also especially in the R&D, on the R&D side. So what's the role of humans in this process?
Yeah, I talked earlier about human augmentation, and if you take smart machines of the future, like I was talking about, that are mobile and reconfigurable and autonomous and connected and working around people, like there's a lot that has to get there on the tech. And you can do a lot more operations in an automated way sooner if you don't require, full-on autonomy. Like, for example, in transportation, we're going to see automated trucking like much sooner than we're going to see like automated taxis, because the problem when constrained is much more achievable with shorter term technology. So what does that require? That requires humans to be in close contact with machines, maybe working in the same space, constantly intervening when something is going wrong. And the human goes from the driver or the operator to the monitor, to the manager, and so then it becomes more of a human machine team. So that role of the human on the ground becomes much more technological, but doesn't go away at all. And then the other part of the human machine team is just, if every machine is going to get a lot more intelligent, you're going to need a lot more engineers to create them. So the engineering involved with designing and integration of these systems becomes much more demanded.
And do you think digital twinning is enough, or at the end there are always some edge cases that only when you deploy the technology in the real world you can find out? For example, in automation or in robotics, you can simulate the full environment, but then there is an interaction between humans and robots in a real world, and something happened. Edge cases that you were not able to simulate. Tell us more about that.
Yeah, I mean, I think you're imagining a digital system that's the design system and the operational system that executes it in the physical world. And we kind of cut it differently. Yes, that needs to happen, but that operational system in the physical world needs to be separated into the stuff that like the absolutely 10-9 reliability constraint system on the machine, and then the much more unpredictable AI parts of the system. So
great. Let me see. I think we have a question from the audience. So they're asking, building on safety and security thread from a few minutes ago, do you physically ensure that a critical part, such as a valve or a motor, is actually in the off position before the next process step takes place?
Would that be a Will question?
I could speak to that from our experience.
Go for it.
We do this a lot. I guess there's two approaches we take for something like this. And of course, we would grade in this case, a valve or a motor in terms of criticality. Sometimes it doesn't really matter all that much. And if it doesn't, then that's great. We don't have to be quite as vigilant. But when it does matter and there's a high criticality, the first approach is a redundancy. So, we'd have two or more sensors, or even two or more types of sensors that work differently, or maybe even on different networks or circuits to avoid sort of interference. And then the other thing we can rely on sometimes is sort of peripheral sensing. So it's often the case that if there's a motor that's just spinning, we can detect, okay, is it spinning or not? Great. But then it's doing something else. So obviously the classic example is motors that have encoders. There's like, am I spinning signal? And then there's like, where am I at signal? And so we can kind of look at these expanding radii of peripheral signals, and some of them can even be inferred. It's like, is the motor running? Oops, is my motor spinning sensors out, but I'm also monitoring total system power consumption. And it looks like the motor's on because we shouldn't be consuming this much electricity. So I kind of think about it in terms of redundancy and then expanding radii of inferred signals or sort of peripheral signals.
Yeah.
Thank you.
Yeah, it's always
jump in it too.
Yeah, it's always that independent level of verification. And sometimes it could be as simple as you said, like a separate system. In the case of a valve, or if I know this leg of piping should never exceed this pressure, then I could put a relief valve on there. That's an independent measurement, independent local measurement, and it goes above that pressure. It says nope, and it just pops open and relieves and saves the system. And so anytime you have those sort of independent checks, and it can be even as complicated all the way up to the rocket says it thinks it's right here as it's flying, and I'm doing an independent measurement, and I agree or I disagree. And if I disagree, I have the ability to enact the following safing of the rocket, right? So you always have that, right? Depending on the level of safety, the independent, and sometimes it is a human. Sometimes the best way is literally a camera that's looking at the system, and I know I can see this very critical valve is like the handle is up, it is off, and so we're safe to approach, or we're safe to engage, or we're safe to proceed into the operation. Absolutely.
Yeah, it's a key part of that, particularly as we get to the integration. I mean, even Elon Musk admitted a few years ago that humans are underrated. So we still need to be in that cycle somewhere as we're doing these integrations. On that one, I kind of want to we've covered a lot of ground up till now in the first 45 plus minutes. I'd like to kind of step back and just do a little futurist kind of approach now and get each one of you to spend a few minutes and really describe what you see this space looking like in 2050. I mean, whether it's additive manufacturing being a key part of it, the advances in optics, drones flying everywhere. Take us to kind of what you think the kind of vision of 2050 is, where you've got a massively integrated digital and physical space. Why don't we just work down the line? Andrew, if you want to jump in first.
Yeah, I'll heavily bend my answer back towards key development, right? So we at Venus are digging way down the technology ladder and trying to make something happen it's pretty bold in a couple of different technology areas. So for us, it's the ability of like, I have an idea how to solve that problem, and it's how fast can I go from that idea to it got implemented and tested and then back again. So my ideal in 2050 is I write on my notepad, the design should go like this and make it cut like this, and this pressure goes up, like, right? I whatever I can slap on paper with my pen, then by tomorrow has been either designed in CAD, and this simulation got kicked off, and this prototype part got printed because it was the key thing that was like, right? So anything I can get down and automate that chain and come back, and right, you want to find out how wrong you are as fast as possible. Right. And that's the terrifying thing about doing hard science, right? Is actually it's knowing that I have to be wrong 60 times and then I'm finally right. And that loop can be terrifying because it can be, right? It could take up to a year, and like, what progress are you making? Well, I'm continually wrong. And like, hallelujah. So anytime you can make that faster, then that's where these breakthroughs can kick loose. And so I take that viewpoint of that so many technologies, if you go look in academia, and so many ideas that are out there, but they're just so not mature that, gosh, if we could make things more mature because we've automated the process between idea to test, I mean, the things that we could solve would become incredible. And there's all sorts of pieces that go onto that, right? Like I said, all the way to that real hardware, making a real test, giving you real data.
What do you think is some of the kind of key technologies we have, those key enablers you just mentioned that we have now, and what are some of the ones we still kind of need to actually get off the shelf to do what you're doing?
I've seen CAD, take an example of computer-aided design, used in horrible ways. I've seen it used as just a more efficient way to make a drawing. And like, that's cringeworthy, because it's like, no, it's in CAD, I can actually make something move, right? Y'all are talking about clearances, right? Can the robot arm clear here? Is there interference, right? So there's things that you can use CAD for, and I've seen people just use it, to a 10th of its power. So there are things we're doing now that 20 years ago, people have been like, wait, that's what you did with this amazing technology? because you made a drawing faster. So I think there are pieces of that you know, the best people, the best ways of using each of that technology that are we doing now? Are we being open and verbal enough about the pains that each one of us founders are having, or each one of us developments are having, to get the most lessons learned out of the existing technology stack that we have, especially because the software world is changing that technology stack on us every 3 years, right? So
Yeah, that's like,
are we actually telling enough stories amongst ourselves to sort of globally move the needle faster on all this stuff?
some kind of knowledge management system that quicker deploys. That's an interesting play. Will, what's your kind of take on where we're at in 2050 and what we need to do to get there?
Yeah, sure. I love thinking about the future. And Andrew, I love this. I want this feature too. This being able to kind of think or speak a validated part just into existence. That's pretty cool. You know, some of the problems we're working on at MODICA are kind of downstream of that and in different gradations. But you know, one of our visions is doing things that can enable basically self-healing, self-organizing microfactories anywhere on Earth and then beyond. And that's the super futurist part is, you know, when we talk about lights out or where do humans work in the loop, I think along the way, there's a lot of work to be done in just decision support and faster validation, and humans are obviously in the loop. And I think they always will be personally for a lot of different areas. But there are some scenarios, so we're beginning to look at manufacturing off-world and Martian base and moon base, like these things are happening, and that's truly lights out. I mean, ridiculously lights out, and it's maybe past 2050, but it's on the horizon at some point where you need to have systems that are really self-organizing and self-healing. They need to be able to fix themselves. They need to figure out how to fix themselves. Like I could talk about this for hours. It's really fun to think about. But I think along the way, there are a lot of practical problems to solve. And, you know, one thing that we're working on is what we call generative automation, which would be a subsequent step to Andrew's kind of just part manifesting, which would be taking an assembly or a part that's been designed in CAD and kind of growing a factory or growing at least one process tool around it. And the point of that is sucking up some of the very manual effort in systems integration. So the linking of all these tools and systems that don't want to talk currently. There's a lot of great tools and ecosystems out there, and more every year, but a lot of them still don't just click together or talk. So that's the piece we're working on. And I think hopefully by 2050, that will have come to fruition.
Something like product health monitoring sensors, kind of they're a combination integration tool, or additive manufacturing kind of play into that space. And how does that become an enabler? Or is it just a very small piece of that?
Well, additive is huge. It's one of our, you know, we lean a lot of weight on that because with additive manufacturing technologies, I didn't come up with this, but we use a lot. The complexity is free, and complexity, you know, traditional like CNC milling or manual milling processes, there's geometries you could never make by any other means. So that's pretty exciting. And that is why I think for advanced manufacturing in the future, additive will continue to grow. It's not going to be relevant to every type of material and process like ever, but it's going to address a lot of those problems. And it's great for us. We focus very heavily on additive and also just CNC because they're digital natives. We talked a little bit about the life cycle earlier of, you know, a 30-year life cycle for some machinery. We use lathes that are from, who knows, the 40s. And I think there's some things you could do. Like, of course, if you're the augmented human, maybe you can have like a digital readout like built in, and you can use the 1930s lathe better. Just kind of fun stuff to think about, but it's newer equipment, I guess, and digital native equipment is much easier to think about putting together.
Nice, thanks. Samuel, you kind of touched on this. Yeah, go for it. So
yeah, unsurprisingly, I think we all have the same vision for the future for 2050. But you know, counterintuitively, I think 2050 looks a lot like 1950 in a weird way, because like before manufacturing had massive consolidation, massive automation, massive offshoring, there was a factory down the street, right? And not everybody, but you could graduate from high school and go get a job at the factory down the street and work there for 40 years and get a pension, right? And like that completely changed with those forces of consolidation, automation, offshoring. And I think, we can have this accordion effect where, it went that way, but then the future, I think, is, hyper-local, hyper-automated, much more atomized, much more specialized, and really manufacturing flowing everywhere. So, the construction site, it becomes a mini manufacturing site. The farm becomes a mini manufacturing site or a big manufacturing site. Same thing with mining and turf care and then manufacturing locally. I mean, it's not like you're going to take an automobile factory and like separate it into 100 little pieces that are like spread across Indiana or something. You're still going to have massive, highly automated spaces for things that it makes sense to do so. But I think especially with what Will is talking about doing with hyper-local factories, if we can have a different manufacturing stack, we can have much more quick design loop, quick manufacturing loop, quick reconfiguration in response to local needs and supply chain fulfillment that's really fast across the variety of goods that people need. And I think like it's not the current manufacturing stack that does that. I mean, I think when like all the talk about IT and OT merger and Industry 4.0 really has to do with taking like the machines of today and like instrumenting them and drawing data on them and making better decisions and doing what we're already doing in a more real-time, more efficient way. To get to that, like, hyper-local, atomized, super competitive kind of format, I think you need like a wholesale overhaul of the entire manufacturing stack that goes from IT to the actual machines, to the human interfaces, to the processes that they're all implementing. And it's not until you have that full stack overhaul and you have that flowed out across, every good, can you have that hyper-local competitive kind of thing. But I think it's exciting to think about getting there, really.
I really appreciate the description y'all just gave. You just completely closed it out, took all my notes, and did a way better job of explaining what 2050 looks like, this distributed, decentralized, different stack manufacturing. I appreciate you all taking some time today, giving us your opinions on kind of where this integration is, where it needs to go, and how you guys are deploying it in your various companies. I'd like to thank our participants too. We're coming to the end of our time here, and I hope everybody got a little bit of something out of this. And from my perspective, I'm a manufacturing guy and I still learned a lot. So again, thanks for your time today. And I really look forward to seeing what y'all can do in the future.
Thank you, Brian.
Awesome. Thanks, Brian.
Thank
Y'all
you.
have a good day.
Thank you.